Another way we can transform the graph of a function is by horizontally shifting it left or right. Let's consider some function f at x. This is usually the graph of a function in some basic library, and let's let c be a constant that's positive. If we take that value c and we add it to the x in a position that I'm going to refer to as the inside, and we'll show you what that means here in just a moment, the effect that it has on the graph is that it actually moves the graph of the function to the left c units. If we subtract c from the x value on the inside of the function, the graph of f will shift to the right. This is counterintuitive. Seeing a plus c on the inside shifts it to the left, and seeing a minus c on the inside shifts it to the right. So this transformation is going to end up moving in a way that feels somewhat backwards from what our logical mind might tell us. In order to apply this transformation, a horizontal shift is going to affect the x values of an ordered pair. And again, the graph is going to move in a direction that is backwards from what our logic might tell us. So let's look at our first example. We're going to start with the graph of y is equal to x cubed and use that to graph the function f at x, which is x minus 2 quantity cubed. Now let's just notice that this minus 2 is in a position that we're going to refer to as the inside. We can tell that it's in the inside because it is receiving the same action as the x. The x value, or the independent variable, is being cubed, and that 2 is in the same position as the x, also being cubed, and that's the indicator that tells me that this is on the inside. When we have a constant being added or subtracted from the inside, that is going to result in a horizontal transformation. To move a graph horizontally, we're going to affect the x values, and these horizontal transformations are going to be backwards from our logic. So we begin with the graph of y is equal to x cubed, and we've memorized that graph to have 3 points of interest, 0, 0, 1, 1, and negative 1, negative 1. The graph of x cubed is somewhat snake-like, oriented vertically. Now because this minus 2 is on the inside, we're actually going to shift this graph to the right 2 units. Again, it's backwards from what our logical mind might tell us. So we're going to take all these points of interest and shift them to the right 2 units. So 0, 0 goes to the right 2 and lands at 2, 0. 1, 1 goes to the right 2 and lands at 3, 1. Negative 1, negative 1 goes to the right 2 and lands at positive 1, negative 1. Now we're going to connect these dots with the vertical snake. Essentially the whole graph, the whole function is shifted to the right 2 units. And this would be our final answer. When the transformations get more difficult, it might be easier to keep track of where those points of interest land in a table. We would start with the original points of interest, 0, 0, 1, 1, and negative 1, negative 1. And in order to apply this transformation on the inside, again, we're going to affect the x values in a way that's backwards from logic. It looks like we might be subtracting 2 from the x values, but that would be logical, and we're going to operate in a way that's backwards from logic. So in order to get the landing spot for these points of interest, we're actually going to add 2 to the x values. And when we perform a transformation that affects the x values, we do not change the y values at all. So for the first ordered pair, when we add 2 to the x to get 2, the y coordinate doesn't change. No change to the y, add 2 to the x, we're going to get 3, 1. No change to the y, but add 2 to the x value, and we land at the ordered pair 1, negative 1. And as you can see, these are the same 3 points of interest that we obtained on our graph. And so to check this answer, we'll take it over to our graphing calculator. We'll input the function y is equal to x minus 2 quantity cubed, and then go over to the graph. It looks like our graph is in the right place, but we do want to verify these points of interest. So we'll use the second calculate feature. So we say second calculate there, and we'll select the value function, number 1, which enables us to input x values. Let's start with the x coordinate 1, and we see that our first ordered pair is in the right spot. We can then just hit the x value 2 and recycle through the value function. When we hit x is equal to 2, we see that y is equal to 0, and that point of interest is in the right spot on our graph. We then hit the x value 3, And we see that the 3-1 ordered pair is also in the correct spot. Let's look at another example. This time we're starting with the graph of the function y is equal to the square root of x, and we're going to perform an inside transformation, a horizontal transformation on that graph to get the graph of g. We remember that y is equal to the square root of x has 3 points that we keep track of, 0, 0, 1, 1, and also 4, 2. The shape of the square root of x graph is something that we've memorized. It looks like half a parabola opening off to the right. The graph of g of x is going to be a transformation of the square root of x. Because this -1 is in the same position as the x, it's under the radical with the x, receiving the same action as the x. This is an indicator that the -1 is inside, which means that this is going to be a horizontal transformation, and any of those horizontal transformations are going to be applied in a way that is backwards from what our logic might tell us. So when we see a -1 on the inside, we might think that it's supposed to go to the left, but that's not correct. Because it's on the inside and backwards, this actually is going to be a transformation to the right one. So the ordered pair 0, 0 moves to the right one and is going to land at the ordered pair 1, 0. The ordered pair 1, 1 moves to the right one and lands at the ordered pair 2, 1. And the ordered pair 4, 2 moves to the right one and lands at the ordered pair 5, 2. Let's then connect the dots with the half a parabola graph opening off to the right. And the final answer should have your points of interest clearly labeled so that it's easy to see that your graph is in the right spot. Let's use the graph of this function to determine the domain and the range of this g of x function and write it in interval notation. The domain of g of x, it appears that the smallest x value that generates graph is going to be x is equal to +1, and then we have graph from that point off to positive infinity. We do include +1 in the domain because there is an ordered pair where x is equal to 1, so 1 is part of the domain. As far as the range is concerned, the smallest y element in this collection of ordered pairs is y is equal to 0, and then we get graph from that point up, so from y is equal to 0 to positive infinity, these are going to make up the range elements. Again, we do include the 0 because there is an ordered pair in this collection that has the y value 0. Now let's check this function on our calculator by going to y equals again, and we'll enter second square root of x minus 1 under the radical. And when we go over to the graph, it does look like our graph is in the right spot, but again, we want to verify our points of interest by selecting second calculate and then the value function. We plug in the x coordinates of our points of interest to see if we have those points correct. And we do have 1, 0. Then we just hit 2 and it automatically cycles us through that second calculate value feature again. Hitting enter, we see that the 2, 1 ordered pair is correct, and then we just hit 5 to see that 5, 2 is also a point on our graph.